Mercury has a tail, not a metaphorical one, a real physical tail made of atoms stripped directly from its surface, stretching tens of thousands of kilometers behind the planet as it swings around the sun. Scientists have been watching it for years, but until recently, no one fully appreciated what it meant. The planet has long been considered the least interesting world in the solar system. Too small, too close to the sun, too ancient, too inactive to hold any modern surprises. Textbooks described it as a dead rock. Planetary scientists used it as a reference for geological termination, as in when a planet has cooled, contracted, and stopped doing anything interesting. It ends up like Mercury. That picture is now incomplete. New data, including the first confirmed detection of lithium in Mercury's exosphere in 2025, has forced scientists to reconsider what the planet still holds and what it is still actively losing. This is not a dramatic rewrite of everything, but it is a genuine correction. Mercury is not inert. It is shedding material in real time through mechanisms that are still running today, and it contains chemical inventories that no one expected it to still have. Understanding why starts with the basics. Mercury is the innermost planet in the solar system. Its average distance from the Sun is about 57 million kilometers, roughly 1/3 the distance Earth sits from the Sun. That proximity has consequences. The solar wind, a constant stream of charged particles emitted by the Sun, hits Mercury with far more intensity than it hits any other planet. Solar radiation is more concentrated. Ultraviolet flux is stronger. The thermal environment is more extreme. All of that matters for what happens on and just above the planet's surface. Mercury's diameter is 4,879 kilometers. That makes it only slightly larger than Earth's moon. Smaller planets cool faster, which is why scientists assumed long ago that any internal geological activity had ceased early in the planet's history. The core cooled, the crust locked in place. Nothing moved below the surface anymore. Its orbit is also unusual. Mercury has the most eccentric and most inclined orbit of any of the 8 planets. Its distance from the Sun swings from 46 million kilometers at its closest point to 70 million kilometers at its farthest. That swing matters because solar intensity changes dramatically across that range. The closer Mercury gets to the Sun, the more aggressively it is bombarded by radiation and charged particles. The orbital eccentricity also has a famous historical connection. Mercury's closest point to the Sun, called its perihelion, shifts slightly with every orbit. Over a century, this shift amounts to 5,599.7 arcseconds. Most of it can be explained by gravitational tugs from the other planets, but 43 arcseconds per century were unaccounted for. For more than 60 years, that number was one of the most stubborn puzzles in astronomy. In November 1915, Albert Einstein submitted what would become one of the most famous papers in the history of physics. His general theory of relativity, applied to Mercury's orbit, predicted precisely 43 arcseconds of perihelion shift per century, with no adjustable parameters. Einstein later described his reaction when the calculation came out correctly. He wrote that he was beside himself with joyous excitement and that he had heart palpitations. The numbers matched. Mercury's orbit had been the first real-world test of general relativity, and it passed exactly. That same extreme orbital path, bringing the planet so close to the Sun at perihelion, is now understood to be one of the key drivers of the modern particle loss scientists are measuring today. The Sun's influence on Mercury at perihelion is intense enough to trigger multiple escape mechanisms simultaneously. The physics that once puzzled Newton is the same physics that drives the atom-by-atom erosion of the planet's surface. Mercury also rotates unusually slowly. It takes 58.6 Earth days to complete one rotation around its own axis. Because of a gravitational locking called the 3-to-2 spin-orbit resonance, the planet completes exactly 3 rotations for every 2 orbits around the Sun. The result is that one solar day on Mercury, measured from one sunrise to the next, lasts 176 Earth days. The sky does something strange because of this. Near perihelion, when Mercury is moving fastest in its orbit, the orbital motion temporarily overtakes the rotational motion. An observer standing on the surface would watch the Sun rise, then slow down, then briefly move backward across the sky before resuming its normal path. This apparent retrograde solar motion is a direct consequence of the orbital geometry, and it happens on no other planet in the solar system under quite the same conditions. Temperature swings on the surface are among the most extreme of any solid body in the solar system. The day side, directly facing the sun, can reach 430 degrees Celsius. The night side drops to negative 180 degrees Celsius. The difference of more than 600 degrees happens without any atmospheric buffer to moderate it. There is no air to carry heat from one side to the other. What receives sunlight burns, what faces space freezes. Despite all of this, despite the solar battering and the extreme heat and the billions of years that have passed since Mercury formed, the planet holds something that should be gone. Multiple elements have been detected in its exosphere that were assumed to have been stripped away long ago, and new measurements are adding to that list. Understanding what those elements are, how they got there, and what they are doing right now requires understanding what the exosphere is in the first place. Mercury does not have an atmosphere. That distinction matters. An atmosphere is a continuous layer of gas held in place by gravity, where pressure builds from the top down and where weather, chemistry, and heat transfer can all happen. Mercury has nothing like this. What it has instead is called an exosphere, an extremely thin layer of individual atoms and molecules that are not dense enough to interact with each other meaningfully. Particles in an exosphere do not behave like a gas. They move independently, following ballistic trajectories above the surface and either falling back down, escaping into space, or being pushed away by radiation pressure. This distinction is important because it changes what you expect to find. In an atmosphere, elements can be recycled, transformed, and retained through chemical reactions and pressure effects. In an exosphere, every particle either falls back down or escapes permanently. There is no recycling mechanism. There is no way to trap atoms that gain too much energy. Whatever is in the exosphere is in the process of being lost. So when scientists detect sodium, potassium, calcium, magnesium, lithium, and other elements in Mercury's exosphere, they are detecting materials that are actively leaving the planet. Sodium was the first element detected in substantial quantities. Its emission line in ultraviolet light is strong enough to be observed from Earth using telescopes equipped with narrowband filters. Scientists began noticing a sodium tail extending behind Mercury in the direction away from the sun. Radiation pressure from sunlight pushes sodium atoms outward. The tail can reach tens of thousands of kilometers in length, and in some observations, it extends even farther, to hundreds of thousands of kilometers, when solar activity is elevated. The tail is not bright or obvious like a comet's dust tail, but it is real, measurable, and consistent. It appears every time Mercury is observed under the right conditions. Potassium was detected next. It escapes through the same mechanism as sodium, but in smaller quantities. The potassium tail is shorter and fainter, more difficult to observe directly, but measurable through high-resolution spectroscopy. Its presence confirmed that the exosphere is not dominated by just one element. Multiple volatile materials were escaping through the same processes. Then came calcium and magnesium, both detected by the Messenger spacecraft during its orbital mission from 2011 to 2015. Calcium is heavier than sodium or potassium, which makes its presence in the exosphere more puzzling. Heavier atoms require more energy to escape. Their presence suggests that the escape mechanisms acting on Mercury are energetic enough to lift not just the lightest materials, but also heavier ones. The detection of abundant sulfur on the surface was equally unexpected. Sulfur is a volatile element, meaning it is relatively easy to remove under heat and radiation. Scientists had assumed that Mercury's extreme proximity to the Sun would have stripped sulfur away early in its history. The Messenger data showed that assumption was wrong. Mercury retained more sulfur than planetary formation models predicted, and that sulfur was concentrated in volcanic deposits across the surface. Now add lithium to the list. Lithium is a light element, the third lightest in the periodic table. It is extremely reactive and does not last long under intense ultraviolet radiation. In 2025, researchers re-examining archival data from Messenger's ultraviolet spectrometer found consistent spectral signals matching lithium's emission lines. The signals were faint, but they were present across multiple observations and did not match any known instrument artifact or contamination source. After ruling out other explanations, the team concluded that lithium is genuinely present in Mercury's exosphere. This matters for a straightforward reason. Lithium is so volatile, and Mercury is so close to the Sun, that lithium should have been eliminated from the surface layers long ago. For any detectable amount to be present today, something must be continuously supplying it. The surface must still contain lithium-bearing minerals that are being broken apart and released by ongoing surface processes. The detection is not just a chemical curiosity, It is evidence that Mercury's surface chemistry is more complex and more volatile-rich than current models account for. The full inventory of exospheric elements as understood today includes sodium, potassium, calcium, magnesium, hydrogen, helium, oxygen, and now lithium. Each element has its own escape profile, its own abundance, and its own set of surface sources. Together, they paint a picture of a planet that is chemically richer than its reputation suggested, and physically more active than the dead rock model allowed. So how does any of this happen? Mercury has not had active volcanic eruptions for an estimated 3 billion years. Its interior has cooled and contracted. The planet has actually shrunk slightly over its lifetime as the core solidified, producing compressional ridges and scarps visible on the surface. There is no internal heat engine driving material up through the crust. There are no hydrothermal vents, no geysers, no plumes, yet material is still escaping. The explanation lies entirely on the surface, and it involves 4 distinct physical mechanisms working simultaneously. The first is micrometeorite impact vaporization. Mercury sits in a region of space that is well populated by interplanetary dust and small rocky particles. These particles are moving fast, typically at speeds of tens to hundreds of kilometers per second relative to the planet. When they strike the surface, they release enormous energy on impact. The collision is so intense that the surface material at the impact site is vaporized instantly. The shock wave that propagates outward from the impact releases atoms from surrounding minerals. If those atoms are light enough, and if the energy from the impact is sufficient, they escape Mercury's gravitational pull and enter the exosphere. Micrometeorite impacts occur constantly. Across the entire surface, the cumulative effect is a steady flux of freshly vaporized atoms entering the exosphere at every moment. The second mechanism is solar wind sputtering. The solar wind, composed primarily of protons and electrons traveling at several hundred kilometers per second, bombards Mercury's surface continuously. When these particles hit a solid surface at high speed, they transfer energy to the atoms in the uppermost layers. Some of those atoms receive enough energy to be knocked out of the crystal lattice that holds them in place. They are physically displaced from the surface, and, if they gain sufficient velocity, they escape into the exosphere. Sputtering is not as energetically violent as a micrometeorite impact, but it operates over the entire sun-facing hemisphere without interruption. The process is more like steady erosion than a series of impacts. It preferentially liberates atoms from the very topmost atomic layers of the crust. The third mechanism is photon-stimulated desorption. Ultraviolet radiation from the sun carries enough energy to break chemical bonds on the mineral surface. When a photon with the right energy is absorbed by a surface atom or molecule, the energy is transferred directly to that bond. If the energy exceeds the bond strength, the atom is released. This process is most effective for loosely bound atoms that are already sitting near the top of the surface layer. Sodium and potassium are particularly susceptible because they tend to be weakly bound to silicate minerals. This is why they are the most abundant elements in the exosphere. The photon essentially does the work of lifting them off. The fourth mechanism is thermal desorption. Mercury's day side reaches temperatures of 430 degrees Celsius. At that temperature, atoms near the surface have significant thermal energy. Weakly bound volatile atoms at or near the surface can reach escape velocity through thermal motion alone. The process is most effective in equatorial regions where solar heating is most intense, and it is enhanced when temperature gradients across the surface create mechanical stress in the minerals, gradually fracturing them and exposing fresh material beneath. Over geological time, repeated cycles of heating and cooling have slowly churned the upper layer of the surface, a process geologists call thermal gardening of the regolith. This continuously brings new material to the surface where other mechanisms can act on it. None of these four mechanisms requires internal heat. None of them requires geological activity. All of them depend entirely on external inputs, the sun's radiation, the solar wind, and the constant rain of interplanetary particles. That is precisely why they have not stopped. They cannot stop as long as the sun continues to shine on Mercury, and as long as the surface contains atoms that can be liberated. The planet's current proximity to the sun, its weak gravity, and its lack of any protective atmosphere all combine to make these processes as efficient as possible. The absence of a magnetic field would make all of this even worse, except that Mercury does have a magnetic field, a surprisingly strong one for a planet its size. Its global dipole field is about 1% the strength of Earth's. That is weak enough that the solar wind can still reach the surface in many places, especially at low latitudes and in the polar regions during periods of solar activity. The magnetic field provides some partial shielding, but it is not strong enough to prevent surface erosion. Instead, it shapes where the solar wind delivers its energy, channeling it towards certain surface regions more than others. This creates spatial patterns in the exosphere, with some areas producing more particle emissions than others. Mapping those patterns is one of the key goals of ongoing and future observations. The hollows deserve particular attention. In Mercury's cratered terrain, there are thousands of features that do not look like anything formed by impact. They are shallow, irregular depressions with sharp edges and bright halos. They appear in clusters, often associated with areas of elevated reflectance, and they are found both in open plains and inside impact craters. Their edges are not eroded or rounded, which typically happens over long timescales on airless worlds. Their sharpness implies they are geologically young. Messenger scientists studying these features called them hollows. The best current explanation is that they form when volatile-bearing materials beneath the surface are removed, causing the surface to collapse slightly inward. The volatile removal is likely driven by the same processes that supply the exosphere: radiation, thermal energy, and micrometeorite bombardment reaching shallow depths into the crust. As the subsurface volatiles escape, the overlying material loses support and subsides, leaving behind a pit surrounded by brighter material that has lost its darker volatile content. The hollows are not just evidence of past activity. Analysis of messenger images showed that some hollows changed in appearance between consecutive observation passes, brightening and expanding over periods as short as 4 years. On geological timescales, 4 years is essentially instantaneous. These are active features, still forming and still evolving today. Machine learning analysis of the full messenger dataset has now catalogued tens of thousands of hollows at various stages of evolution. Young hollows are crisp, bright, and sharp-edged. Older ones are more faded and their margins are less distinct. The range of ages visible on the surface confirms that hollow formation is an ongoing geological process, not a relic of an ancient era. Mercury's surface is still changing. The connection between the hollows, the surface volatile inventory, and the exosphere is now reasonably well established. The same materials that form the hollows when removed from below are also the materials being detected above the surface. The subsurface volatile reservoir is being depleted from 2 directions simultaneously. From below, where hollows grow as material sublimates outward, and from above, where radiation and solar wind strip the uppermost surface layers and launch atoms into the exosphere. The picture that emerges is not of sudden or explosive activity. It is slow, quiet, and continuous. Mercury is being eroded from multiple directions at once, and the scale of that erosion, while gradual on any human timescale, is measurable and ongoing. Now consider the spacecraft record. Before Messenger, the only close-up data on Mercury came from Mariner 10, which flew past the planet 3 times in 1974 and 1975. The images were low resolution by modern standards, and the flybys were brief. The spacecraft revealed a heavily cratered surface that closely resembled the Moon, a weak magnetic field, and a thin exospheric signal of helium. Nothing in the data challenged the prevailing view of Mercury as a geologically dead world. The pictures showed a static surface. Scientists accepted what they saw. Messenger changed all of that. The spacecraft, launched in 2004, did not enter Mercury's orbit until 2011, after a series of gravity assists around Earth and Venus. Once in orbit, it operated for 4 years before being intentionally crashed into the surface in April 2015 when it ran out of propellant. In that time, it returned more data about Mercury than all previous missions combined. Messenger mapped the entire surface in detail. It measured the composition of the exosphere with a suite of spectrometers. It found the sulfur-rich volcanic deposits, the hollows, the abundant sodium tail, and the range of elements in the exosphere. It confirmed the polar ice deposits in permanently shadowed craters, a finding that had been suspected from Earth-based radar observations, but had never been directly confirmed. It measured the internal structure, confirming the large iron core that makes Mercury disproportionately dense for its size. The planet is roughly 60% iron by volume, with a relatively thin outer shell of rock. But Messenger also left questions unanswered. Its orbit was polar and elliptical, which gave it better coverage of the northern hemisphere than the southern. Its instruments were powerful, but not specifically optimized for tracking rapid changes in the exosphere over short time periods. And the mission ended before all of the data could be fully analyzed, which is why the lithium detection came from a reanalysis of archival data in 2025, a decade after the spacecraft had gone silent. The successor mission is BepiColombo. BepiColombo is a joint mission between the European Space Agency and the Japan Aerospace Exploration Agency. It was launched in October 2018 and has been traveling toward Mercury ever since, using gravity assists from Earth, Venus, and Mercury itself to shed enough energy to enter Mercury's orbit. The mission is named after Giuseppe Colombo, the Italian mathematician who first identified Mercury's 3-2 spin-orbit resonance and proposed the gravity assist trajectory that made Mariner 10's mission possible. By the time of the lithium detection, BepiColombo had already completed 6 flyby maneuvers of Mercury, each one tightening its approach trajectory. During those flybys, instruments on both spacecraft that compose the mission, the European Mercury Planetary Orbiter and the Japanese Mercury Magnetospheric Orbiter, captured data, including thermal infrared maps using the MERTIS instrument. Those thermal maps are revealing. They show that Mercury's surface is not thermally uniform. Different regions heat up and cool down at different rates, which reflects variations in composition and structure across the crust. Some of the hottest zones in the maps align with regions where exospheric particle density is elevated. This suggests that localized differences in surface chemistry may create hotspots for volatile emission. These are not dramatic eruptions. They are subtle spatial variations in particle loss rate, but they are measurable. BepiColombo is expected to enter Mercury's orbit in late 2026. Once in orbit, both spacecraft will operate simultaneously, giving scientists 2 distinct vantage points to observe the planet at the same time. That simultaneous 2 spacecraft geometry has never been used at Mercury before. It will allow researchers to distinguish between local and global changes in the exosphere, to track how particle populations shift during solar events, and to connect what is being lost from the surface to what is building up in the exospheric tail, the suite of instruments. Aboard the Mercury Planetary Orbiter includes spectrometers that can detect individual atomic species in the exosphere, ion analyzers that can measure the energy and composition of particles escaping into space, a magnetometer to map the internal magnetic field structure, and a high-resolution camera system. The Mercury Magnetospheric Orbiter focuses specifically on the magnetic environment, tracking how the solar wind couples to the planet's field and how that coupling drives particle loss. Together, the 2 craft will provide the most detailed picture of Mercury ever attempted. The timing of the lithium detection matters in this context. The fact that it came from archived messenger data suggests the signal was there all along, but the analytical tools and attention needed to extract it from the noise were not applied until recently. That raises a question that is not hypothetical. What else is in the messenger dataset that has not been found yet? Researchers are actively going back through the messenger archive with new computational tools, machine learning classifiers, and updated spectral libraries to search for elements and features that were missed the first time. This kind of retrospective analysis has already produced new findings about hollow distribution and surface mineral mapping. Further chemical detections in the exosphere are possible. Meanwhile, BepiColombo's instruments are calibrated to a much higher standard than Messenger's spectrometers for certain measurements. The lithium detection may have been at the edge of Messenger's capability. BepiColombo, once in orbit, should be able to confirm it clearly and extend the search to other elements that might be present in even smaller quantities. Aluminum, barium, strontium, and manganese are among the candidates that have been discussed in the scientific literature as possible exospheric constituents that have not yet been confirmed. There is a broader scientific reason why Mercury matters beyond the planet. Itself, exoplanet surveys have now catalogued several thousand confirmed planets orbiting other stars, and a large fraction of those are small rocky worlds orbiting very close to their stars. These planets, which include the so-called super-Earths and lava worlds detected by space telescopes, are bathed in radiation and stellar wind in conditions that are, in many cases, more extreme than Mercury's environment, but qualitatively similar. Understanding how a rocky body loses material under intense stellar bombardment requires a test case close enough to study in detail. Mercury is that test case. The rate at which Mercury loses sodium, potassium, or lithium can be measured directly. From those measurements, scientists can build models of surface erosion that apply to comparable worlds around other stars. This is relevant not just for the physics of planetary surfaces, but for the question of atmospheric persistence. Many exoplanet researchers want to know whether small rocky planets near their stars can retain meaningful atmospheres, or whether stellar radiation strips them bare over geological timescales. Mercury, which has clearly lost its atmosphere and is still actively shedding surface material, provides a data point at the extreme end of that spectrum. It also informs models of planetary formation. The fact that Mercury retains volatile elements like sulfur, sodium, potassium, and lithium, despite its location and age, constrains how much volatile depletion actually occurred in the inner solar system during the early era. Some models of solar system formation predict that the region where Mercury formed should have been almost entirely depleted of volatiles. The measured abundances suggest those models are too aggressive. Some volatiles survived in the inner solar system, and they survived in quantities detectable today, billions of years later. Mercury's oversized iron core remains one of the deepest puzzles in planetary science. The planet's density is 5.4 grams per cubic centimeter, second only to Earth among the planets, and Earth is much larger, which compresses its interior more. Mercury's density is disproportionately high for its size, which can only be explained if its core is very large relative to its total volume. Current estimates place the iron core at roughly 85% of the planet's radius, leaving only a thin outer mantle and crust. Why is the core so large? The leading explanations involve either a giant impact early in Mercury's history that stripped away most of the original mantle, or a process in which the original disk of material that formed Mercury was sorted by the sun's radiation, such that it preferentially collected heavy metallic particles over lighter silicate ones. Neither explanation is fully satisfying. Both make specific predictions that can be tested by measurements of the planet's gravity field and internal structure, and BepiColombo is equipped to make those measurements more precisely than MESSENGER could. The crustal composition, which is linked directly to the volatile inventory and the exospheric emissions, is also tied to the core question. If Mercury's mantle was stripped early by an impact, then the surface chemistry should reflect that. If the original volatile depletion was caused by solar heating of the disk, then the crust should have a different compositional signature. Understanding what is still in the crust and what is being lost today is part of the chain of evidence that leads back to how the planet formed. And then there is the ice. Mercury has permanently shadowed polar craters. Because of the planet's nearly zero axial tilt, the floors of deep craters near the poles never receive direct sunlight. Temperatures in those permanently shadowed regions can drop to negative 200 degrees Celsius or lower. Radar observations from Earth detected anomalously bright reflections from those polar regions in the early 1990s, and scientists hypothesized that the brightness could be explained by water ice. MESSENGER confirmed it. The polar deposits contain hundreds of billions to perhaps 1 trillion metric tons of water ice, buried under a dark lag layer of organic-rich material that acts as an insulating blanket. The ice has likely been accumulating over billions of years, delivered by comets and asteroids that struck the planet and released volatiles that eventually migrated to the cold polar traps. The coexistence of extreme heat and stable ice on the same small planet is one of the stranger aspects of Mercury's environment. On the day side at the equator, surface temperatures exceed the melting point of lead. At the same time, within a few thousand kilometers, in the shadowed crater floors, water ice has persisted for billions of years. This contrast captures something essential about Mercury. It is a world of extremes, where the same conditions that create devastation in one region enable preservation in another. Understanding how the polar ice interacts with the rest of the volatile system is an open question. Does evaporation from the ice deposits, even at extremely low rates, contribute to the exosphere? Are any of the atoms detected in the exosphere traceable to polar sources rather than equatorial surface processes? These questions have not been answered. They require precisely the kind of spatially resolved exospheric measurements that BepiColombo is designed to provide. What scientists expect to learn from BepiColombo's orbital phase over the years ahead encompasses multiple open problems simultaneously. The three-dimensional structure of the magnetic field will be mapped in detail, helping to determine whether the unusual offset of Mercury's magnetic dipole from the planet's center is caused by a layered outer core structure or some other internal geometry. The surface will be imaged at resolutions better than MESSENGER could achieve over certain regions, particularly in the southern hemisphere. The exospheric composition will be measured with higher sensitivity, potentially revealing additional trace elements and tracking how the entire system responds to solar activity on timescales from hours to years. There is also the question of what the hollows are actually made of. The volatile minerals that sublimate to create them have not been directly identified with certainty. Candidate materials include magnesium sulfide, calcium sulfide, and possibly other light-absorbing sulfur-bearing compounds. The spectral signature of fresh hollow material, the bright halo surrounding the pit, is distinct enough that it should be identifiable with BepiColombo's spectrometers if the orbital geometry is favorable. Knowing exactly what is sublimating could help connect the hollow-forming process to the specific atomic species detected in the exosphere. One thing that is now clear is that Mercury is not done telling us things. Every mission that has visited the planet has returned data that contradicted existing models. Mariner 10 showed a weak magnetic field that theory said should not exist. MESSENGER showed volatile elements that formation models said should be absent. Archival reanalysis showed lithium that no one was looking for. BepiColombo will show something that is not yet anticipated. That pattern is not unusual in planetary science. Every time a new instrument reaches a new environment, the data comes back with something unexpected. But Mercury has been particularly consistent in this regard. It has surprised every mission that has visited it every time. Part of the reason is that it occupies an extreme position in the solar system, the most eccentric orbit, the largest relativistic effects, the closest proximity to the Sun for a planetary body, the largest iron core by proportion. Extreme environments produce phenomena that do not occur under milder conditions. They reveal physics that stays hidden in less intense settings. Mercury is not important because it is dramatic or because its findings are shocking. It is important because it is a data point at an extreme that cannot be approximated in a laboratory or replicated in a model without measurements from the real object. It tests theories of planetary formation, atmospheric loss, surface chemistry, and magnetic field generation in conditions that no other solar system body provides. And it is doing all of this while actively shedding material into space, right now, through mechanisms that are running continuously and that will continue to run until the Sun eventually expands and changes the environment entirely. On human timescales, the changes are imperceptible. On geological ones, they are cumulative and significant. On the timescale of a single spacecraft mission, they are measurable enough to give scientists the data they need. What remains unknown is extensive. The exact rate of volatile loss integrated over the full surface, the complete inventory of trace elements in the exosphere, the precise mineralogical identity of the hollow-forming compounds, the three-dimensional structure of the internal magnetic field and what it implies about core stratification, the mechanism that allowed volatile elements to survive in the inner solar system in the quantities MESSENGER found, the origin and total mass of the polar ice deposits, the history of solar activity that drove the current exospheric state, whether any of the exospheric chemistry has analogues on other planets in other stellar systems. These are specific, measurable, answerable questions. They are not philosophical. They have experimental solutions. BepiColombo is on its way to answer as many of them as its instruments allow. The archival MESSENGER data is being remined with new tools. Ground-based observations continue to monitor the sodium, tail and other observable features during Mercury's periodic appearances in the evening or morning sky. Mercury is a world that was dismissed for decades. It was assumed to be understood. It turned out not to be. The assumption was not unreasonable, given what was known at the time, but the evidence has moved steadily in one direction. The planet holds more than expected. It releases more than expected. It still changes, still reacts, still sheds. The old story was that Mercury was finished. The current data says that story was premature. If you find yourself more curious about planetary science, the physics of exospheres, or the ongoing results from BepiColombo, that curiosity is worth following. Liking and subscribing helps make sure you see the next installment when new data arrives. Mercury's orbital insertion is coming. When it happens, the science will move quickly. The current moment in Mercury science is unusual because the timing of several developments aligns. New detections from archival data, an active spacecraft closing in on orbital insertion, and a growing recognition that the inner solar system is chemically richer and more dynamically active than previously thought. That alignment does not happen often. When it does, the resulting observations tend to redefine the standard picture for the next generation of planetary scientists. Mercury spent decades as a dead world in the textbooks. It is now the most instrumented rocky body in the inner solar system, after Earth. What those instruments are about to find will be worth paying attention to. The story of how scientists came to understand Mercury's magnetic field is worth examining in detail, because it follows the same pattern that defines Mercury science as a whole. An anomaly discovered, a theory proposed, the theory tested against reality, and reality winning. When Mariner 10 flew past Mercury in February 1974, it carried a magnetometer. The expectation was that Mercury would have no significant magnetic field. Planetary magnetic field theory at the time held that a field required a rapidly rotating liquid iron core. Earth's magnetic field is generated by convective circulation in its outer liquid iron core, driven by heat escaping from the inner solid core. Mars and the Moon, both small and slow, have no global magnetic field today. Mercury, being smaller than Mars and rotating extremely slowly, seemed to fit the same category. No dynamo, no field. What the magnetometer measured was unexpected. Mercury had a global dipole magnetic field. It was weak, about 1% of Earth's field strength, but it was clearly there and clearly organized. Mariner 10 confirmed this across its 3 flybys. Mercury had a magnetosphere. The solar wind was deflected by a magnetopause, just like at Earth, though compressed to a much smaller scale because the field was weaker. Theorists scrambled to explain it. Some proposed a remnant crustal field, similar to the magnetic striping found in Earth's seafloor, preserved from a dynamo that was active long ago but had since shut down. Others argued that some form of dynamo must still be operating, either in a thin fluid outer core shell or through some mechanism not yet well understood. MESSENGER resolved some of this. Its magnetometer measurements showed a clear global dipole, but with a striking peculiarity. The magnetic North Pole is displaced northward from the planet's geographic North Pole by about 480 kilometers. This offset is far larger than Earth's magnetic offset and cannot be explained by a simple spherical dynamo. It requires a more complex internal field structure, possibly one in which the fluid outer core has layered composition, with a denser iron sulfide layer at the bottom and a lighter iron layer above, each contributing differently to the total field geometry. This so-called stably stratified layer model predicts that convection in the outer core is suppressed in certain regions, producing a field that is shifted and asymmetric rather than centered on the planet's rotation axis. The model makes specific predictions about higher-order components of the field, meaning the more complex mathematical terms beyond the basic dipole that can be tested with precise measurements. BepiColombo's dual magnetometers, operating simultaneously from 2 different orbital altitudes, will provide exactly the kind of high-resolution field maps needed to test this model. The magnetic field also interacts with the exosphere in ways that create spatial patterns in particle emission and loss. Where the field is weak enough that solar wind particles can penetrate to the surface, sputtering rates are higher. Where the field is stronger and more protective, the surface is more shielded. During geomagnetic substorms, which occur on Mercury as well as Earth, when energy stored in the magnetosphere is suddenly released, particle bombardment of the surface can spike dramatically. MESSENGER observed these events, called magnetic reconnection events, occurring far more frequently at Mercury than at Earth because Mercury's magnetosphere is so compressed by the stronger local solar wind that it reaches an unstable state much more often. During one of BepiColombo's early flybys, scientists detected what appeared to be a period of elevated exospheric density coinciding with elevated solar wind pressure. The temporal resolution was limited because the flyby was brief, but the suggestion was that the exosphere responds dynamically to solar conditions, not just statically to average solar exposure. Once in orbit, BepiColombo can monitor this in real time, tracking the exosphere as solar storms pass through the inner solar system and watching whether particle emission rates climb and fall. With the incoming particle flux, this connection between space weather and surface erosion is not just scientifically interesting, it is quantitatively important. The total lifetime erosion of Mercury's surface depends heavily on how often and how intensely solar storms have hit the planet over the past 4 billion years. The Sun was more active early in its history, when it was younger and its radiation output was less stable. Mercury's surface has been exposed to that early high-activity period. The cumulative erosion over geological time may be many orders of magnitude larger than the current slow rate suggests. Understanding the current rate and its sensitivity to solar activity is the first step in reconstructing the total historical erosion budget. That budget connects directly to the hollow formation problem. Hollows grow when volatiles escape from subsurface deposits. The total volatile inventory of Mercury's crust that is accessible to this process is finite. If the erosion rate can be measured accurately, and if the size and number of hollows can be used to estimate how much material has already been removed, then scientists can estimate how long the volatile reservoir has been depleting and how much might remain. Some geologists studying the hollow dataset believe the total volume of material removed to form all observed hollows represents a small fraction of the overall volatile content of the outer crust. If true, the process has much longer to run. Others think the accessible shallow volatile inventory may be more nearly depleted in some regions, with hollows in those areas entering a slow phase of gradual darkening as the remaining material exhausts itself. Distinguishing between these scenarios requires knowing the local volatile concentration, the local erosion rate, and the mineralogy of the hollow-forming compounds, none of which is fully characterized. The sulfur story is also not finished. Messenger's X-ray spectrometer detected sulfur concentrations on the surface that were higher than any other rocky planet, relative to the overall composition. This was surprising because sulfur is volatile and should have been depleted in the hot inner solar system during planetary formation. The prevailing explanation is that Mercury formed from material that was somehow retained from the volatile, rich outer regions of the original solar nebula, possibly through a process in which Mercury migrated inward from a more distant initial orbit before settling into its current path. This migration hypothesis connects Mercury's volatile abundance to broader models of how the solar system's architecture evolved in the first few 100 million years. The NICE model and the Grand Tack hypothesis, two major frameworks for explaining the large-scale orbital reorganization of the solar system in its early history, both involve significant migration of Jupiter and Saturn in their early phases. Those migrations sent shockwaves through the inner solar system, scattering asteroids and potentially reshuffling the orbital positions of the terrestrial planets as well. Mercury may have participated in that early dynamical chaos, beginning its life at a larger orbital radius and subsequently being pushed inward to its current extreme position. If true, Mercury's surface chemistry preserves a record of the materials available at larger radii, which would explain the volatile abundances. The sulfur, the alkali metals, the lithium now detected, all of these could be relics of a formation location that was farther from the Sun than where Mercury sits today. The planet carried that volatile inventory with it as it migrated and has been slowly losing it ever since, but not completely, not yet. This is the most important implication of the ongoing volatile detections. They are not just chemical curiosities. They are forensic clues about where Mercury formed and how the inner solar system evolved. Every element detected in the exosphere is a data point in a much larger argument about the origin and history of the planets. The detection of lithium fits into this framework precisely. Lithium is the lightest metal. In the standard model of planetary formation in the inner solar system, lithium should be depleted from a body as close to the Sun as Mercury now sits. Its detection implies either that Mercury retained lithium from a formation zone where it was more abundant, or that some lithium was delivered to Mercury later by impacts, or both. Each of these possibilities carries different implications for the overall volatile inventory. Distinguishing between them requires measuring the isotopic ratio of the lithium in the exosphere, since different sources tend to have characteristic isotope signatures. That measurement is at the edge of what current instruments can achieve, but it is a defined goal for future analysis. Isotope measurements in planetary exospheres are challenging because the signals are weak and the differences between isotopes are small. Sodium, for instance, has two stable isotopes, sodium-23, which is by far the more abundant, and none of the others matter for this discussion. But lithium has two stable isotopes, lithium-6 and lithium-7, with a natural ratio that varies between cosmic, geological, and biological sources. A measurement of the lithium isotope ratio in Mercury's exosphere would directly constrain whether the lithium is primordial, meaning it was there from the formation of the planet, or secondary, meaning it was delivered later by impactors. No such measurement has been made yet. It is a defined future goal. Calcium in the exosphere presents its own puzzle. Calcium is significantly heavier than sodium or potassium. In principle, the same escape mechanisms should work for calcium, but they should be less efficient because the heavier atom is harder to lift. Yet calcium is detected at abundances comparable to some of the lighter species. One explanation is that calcium is being released in molecular form as calcium-bearing compounds rather than single atoms, which would then dissociate in the exosphere. Another is that micrometeorite impacts, which can release energy sufficient to vaporize even heavy elements, are the dominant source of calcium rather than the gentler photon and sputtering processes that work well for lighter atoms. Distinguishing between these sources requires measuring the spatial distribution of calcium in the exosphere and comparing it to the distribution of micrometeorite impact flux, which is non-uniform across the planet. Some regions receive more micrometeorite impacts than others because of the geometry of Mercury's orbit and the distribution of interplanetary dust in the inner solar system. If calcium abundance peaks in high-impact flux regions, the impact vaporization hypothesis is supported. If it is more uniformly distributed, the molecular release mechanism becomes more plausible. Messenger's orbital inclination gave it excellent northern hemisphere coverage but limited southern hemisphere views. Calcium distribution mapping across the full globe was therefore incomplete. BepiColombo's orbital geometry, combining the two spacecraft at different inclinations and altitudes, will provide more uniform coverage. Full global maps of calcium, sodium, potassium, and lithium distribution in the exosphere are among the primary science goals for the mission's orbital phase. The oxygen story in Mercury's exosphere is also worth noting. Oxygen has been detected, and in some observations it appears at unexpectedly high abundances relative to the other species. Oxygen could come from solar wind particles that penetrate to the surface and react with mineral oxides, releasing oxygen atoms. It could also come from photodissociation of surface hydroxyl groups, which might form when hydrogen from the solar wind reacts with oxygen-bearing minerals. The relative importance of these sources is not established. Oxygen in the exosphere is not a sign of biological activity. It is a byproduct of purely physical and chemical processes operating on a bare rock. But the exact mechanism of oxygen release tells scientists about the specific mineral reactions occurring on the surface, which again connects to the broader question of surface composition. Then there is the question of water itself. The polar ice is established, but is there any water anywhere outside the polar cold traps? Earth-based observations and some messenger data have hinted at possible hydroxyl groups, the OH molecule in the equatorial regolith, preserved in shadowed micron-scale pits on grain surfaces. This is the same kind of water detection that surprised scientists when it was confirmed in the lunar regolith. The moon was also considered dry, and it turned out to have trace amounts of water molecules and hydroxyl groups widely distributed across its surface, delivered by solar wind hydrogen reacting with oxygen in the soil. Mercury may have the same. The evidence is not conclusive, but the possibility that trace hydration exists in Mercury's equatorial regolith, even at a level far below anything detectable from orbit, changes the chemistry of the surface significantly. Hydroxyl groups are reactive. They participate in chemical reactions that can alter the binding energies of surface atoms, potentially affecting which elements are preferentially released into the exosphere and which are retained. If Mercury's surface has a thin layer of reactive chemistry operating continuously, the escape mechanisms may be more complex than the simple physical models currently describe. All of this scientific complexity resolves back to a central point. Mercury is a live experiment in planetary geochemistry and space physics, operating under conditions that cannot be replicated elsewhere in the solar system. It is simultaneously losing material, accumulating ice, forming new surface features, being bombarded from space, and interacting with its own magnetic field in a compressed, dynamic magnetosphere. None of these processes have stopped. All of them are accessible to measurement with current or near-future instruments. The fact that these processes can be studied in such detail is an unusual privilege of living in the one planetary system where we can send spacecraft to do close-up measurements. Most of what we know about rocky exoplanets comes from transit observations that can tell us about size and atmospheric absorption features, but nothing about surface chemistry or particle loss rates. Mercury gives us a calibration point that no telescope can provide by looking at a distant star system. And there is something appropriate about Mercury being the planet that constantly surprises us. It is the closest to the Sun, the smallest, the most eccentric, the most extreme. If any planet were going to reveal that the standard models were wrong, it was always going to be the one that lives at the edge of what the solar system's physics can produce. Extreme environments strip away comfortable assumptions. Mercury has been doing that to planetary science since 1974. What BepiColombo will find when it finally settles into orbit and begins its systematic survey is genuinely unknown. The instruments are the best ever sent to Mercury. The science team is the largest that has ever focused on the planet simultaneously. The data pipeline is designed to return more information per unit time than Messenger could. The community has spent the last decade identifying exactly which questions need answers and designing the observations to get them. Some of those answers will confirm existing theories. Others will extend them. A few will probably require revisions. That is how planetary science works. Mercury will keep being Mercury, unexpected and surprising, until the instruments are good enough to explain it fully. And that time has not arrived yet. The planet is losing atoms right now. Lithium, sodium, potassium, and calcium are streaming away from the surface as you read this, pushed by photons and solar wind into thin exospheric halos and trailing tails. The hollows are still growing, slowly, at rates too small to see in a human lifetime, but confirmed across 4 years of spacecraft data. The polar ice is sitting in the dark, preserved by geometry alone, while the equatorial surface bakes at temperatures that would melt tin. None of this is metaphorical. It is physics, running continuously, measurable by instruments, documented in peer-reviewed data. Mercury is the nearest example of a planet being actively shaped by its stellar environment, and the science that describes it has implications for every rocky world orbiting close to any star in the galaxy. The tools to understand it fully are almost in place. The questions are clearly defined. The answers will come from orbit. The relationship between Mercury's surface temperature extremes and its chemistry is worth exploring more carefully, because the scale of those extremes shapes every other process happening on the planet. At 430 degrees Celsius, the dayside surface is hot enough to melt lead. Lead melts at 328 degrees Celsius. Mercury's equatorial dayside exceeds that by more than 100 degrees. Zinc melts at 419 degrees Celsius. Mercury's dayside exceeds that too. Standing on the dayside equator of Mercury at perihelion, you would be on a surface hotter than the melting point of multiple metals, exposed to a sun that appears more than 3 times larger in diameter than it does from Earth, and bombarded by a solar wind of charged particles moving at several hundred kilometers per second. At the same time, 120 kilometers north or south, in a permanently shadowed polar crater, water ice would be sitting in perfect stability at negative 200 degrees Celsius, frozen there for billions of years without any mechanism to disturb it. This contrast is not incidental. It shapes how scientists think about the volatile inventory and the escape processes. The volatiles that are escaping from the dayside are escaping precisely because of the extreme heat. The volatiles preserved at the poles are preserved precisely because of the extreme cold. The same planet, the same geology, the same original chemical inventory, partitioned into burning loss and frozen preservation by nothing more than geometry. This makes Mercury a natural laboratory for studying the boundary conditions of volatile retention on rocky bodies. Where is the line between a surface region that retains volatiles and one that loses them? On Mercury, that line is sharp and geometrically defined. At the poles, permanently shadowed craters preserve whatever volatile material migrates into them. Everywhere else, the surface is too hot for volatile stability. The line is essentially the edge of permanent shadow. Earth's moon is similar, but less extreme. The moon also has permanently shadowed polar craters with ice deposits, and its dayside surface reaches temperatures well above the stability threshold for most volatiles. The difference is that Mercury's proximity to the Sun makes everything more intense. The dayside temperatures are higher. The thermal cycling is faster due to the shorter solar day in some regions near the poles, and the radiation flux is greater. Mercury is the moon dialed up to a more extreme setting. This comparison to the moon is scientifically productive. Both bodies are airless. Both have polar ice deposits. Both have exospheres dominated by sodium and potassium, and both are being slowly eroded by micrometeorite impacts and solar wind sputtering. The difference in scale and intensity between the two gives planetary scientists a way to test whether the escape and retention models scale predictably with solar proximity and surface temperature. If the physics is well understood, It should work for both bodies and produce results consistent with the measured abundances. Messenger's measurements and ongoing lunar science provide the data to test this. One finding that has emerged from this comparison is that Mercury's sodium abundance in the exosphere is, per unit surface area, somewhat higher than the Moon's, which is consistent with Mercury receiving more intense solar radiation and micrometeorite bombardment at its closer orbital distance. The scaling is not perfectly linear because the surface chemistry differs between the two bodies, but the qualitative trend is correct. This gives researchers confidence that the physical models are capturing the right mechanisms, even if the quantitative details need refinement. Returning to Mercury's interior, the question of what the core is actually doing today matters more than it might seem. The magnetic field requires a fluid outer core layer that is still conducting electricity and has enough convective motion to sustain a dynamo. That means the core has not fully solidified. Mercury still has a partially liquid interior, even though it is the smallest of the terrestrial planets and should have lost its internal heat faster than any of them. The likely explanation is that the core's freezing point is suppressed by the presence of lighter elements mixed into the iron. Sulfur, carbon, silicon, and hydrogen can all lower the melting temperature of iron significantly. If Mercury's core contains any of these light elemented mixtures in sufficient quantity, the outer core can remain liquid, even at temperatures that pure iron would have solidified at billions of years ago. Sulfur is the leading candidate given the high sulfur abundance measured at the surface, but confirming the light element identity in the core requires geophysical measurements of the core's density and seismic properties, which spacecraft cannot yet make at Mercury. The core's composition also affects the magnetic field geometry. Different light elements produce different convection patterns in the fluid outer core. Sulfur produces one kind of layering, carbon another. The specific geometry of the magnetic field, including the offset that Messenger measured, constrains which compositions are plausible. BepiColombo's precision field measurements will tighten those constraints further. All of this feeds back into the formation story. The amount of sulfur in the core depends on how much sulfur was available when Mercury accreted. That depends on where in the solar nebula Mercury formed. Mercury's formation location, whether it was always in the inner solar system or started farther out and migrated inward, is one of the most actively debated questions in planetary science. The answer affects how we interpret the core composition. The surface volatile abundance, the magnetic field geometry, and even the total planetary mass budget. The shrinkage of Mercury over its lifetime is another physically interesting consequence of the large iron core. As the core has cooled and partially solidified over the past 4 billion years, it has contracted. The crust and mantle, which are relatively incompressible compared to the core, have responded to that contraction by buckling and faulting, creating a network of compressional ridges and scarps visible across the surface. These features, called Lobate scarps, are one of the most distinctive landforms on Mercury. Messenger found that Lobate scarps are globally distributed, not just confined to certain hemispheres or regions. This means the core cooling and contraction have been affecting the entire planet. Estimates based on the total length and displacement of the scarp network suggest Mercury has shrunk by somewhere between 5 and 10 kilometers in radius since it formed. That is a small fraction of its total radius, but it is geologically significant. The shrinkage is not over. The core is still partially liquid, which means it is still cooling, and as it continues to cool, it will continue to contract slightly. The lobate scarps may still be growing at rates too slow to detect over a spacecraft mission lifetime, or they may already be tectonically inactive. The question of whether Mercury has current tectonic activity, even at an extremely slow rate, is open. If the scarps are still growing, that growth could expose fresh surface material along the fault planes, potentially creating localized regions of enhanced volatile release. Identifying active fault zones is another goal for BepiColombo's imaging campaign. The interplay between the magnetic field, the solar wind, and the exosphere has a specific feature called cusp precipitation that deserves mention. Mercury's magnetic field has cusps at high latitudes, regions where field lines converge and where charged particles from the solar wind can access the surface more directly. These cusp regions experience enhanced bombardment compared to other latitudes, producing measurable enhancements in exospheric density above the cusps. Messenger detected this effect. The northern cusp was well characterized due to MESSENGER's orbital coverage, but the southern cusp was much less studied. BepiColombo will provide the first detailed measurements of the southern magnetic cusp. If the cusp precipitation effect is symmetric between north and south, as expected for a centered dipole, the measurements should match. The known offset of the magnetic dipole northward predicts that the northern cusp is actually weaker than the southern cusp in terms of precipitating particle flux, because the field is stronger and more organized at the north. If the southern cusp is more intense, it should produce more sputtering and more particle injection into the exosphere from that hemisphere. This is a testable, specific prediction that the mission can confirm or refute. The exosphere also carries information about the history of solar activity. The Sun goes through roughly 11-year activity cycles, with periods of higher and lower flare and coronal mass ejection rates. Mercury is the inner solar system body closest to the source of these events. During solar maximum, coronal mass ejections hit Mercury with higher frequency and greater intensity. These events can temporarily compress the magnetosphere to the point where the solar wind directly impacts the surface at latitudes that are normally shielded, producing brief spikes in particle emission rates. Scientists have reconstructed some of the historical solar activity record from measurements of energetic particle deposits in terrestrial and lunar records. Extrapolating those reconstructions to Mercury gives a rough picture of how strongly the planet has been bombarded over different epochs. The current period is roughly average in terms of solar activity, which means the exospheric measurements being made now represent a baseline state, not an extreme. BepiColombo will observe Mercury across at least one partial solar activity cycle, spanning from near minimum conditions towards solar maximum, giving scientists a real-time record of how the exosphere responds to changing solar input. The nitrogen question is occasionally raised in Mercury discussions, though it is more a null result than an active finding. Nitrogen is absent from Mercury's exosphere at any detectable level. On Earth, nitrogen is the dominant atmospheric gas. On Mars and Venus, it is present but less dominant. On Mercury, it is simply not there. This is consistent with Mercury's formation in the hot inner solar system, where nitrogen-bearing ices would not have been available, and with the efficiency of solar wind erosion in removing any nitrogen that might have been delivered by early impacts. The absence is physically informative. It tells us that whatever volatile delivery occurred at Mercury was dominated by rocky, sulfur-bearing bodies rather than volatile-rich icy bodies from the outer solar system. This contrasts with what the polar ice presence suggests about water delivery. If water arrived at Mercury's poles from cometary or outer solar system sources, why did nitrogen not accompany it? The answer likely lies in the very different stability of ice at Mercury's poles compared to the equatorial surface. Water ice, once trapped in a cold permanent shadow, is stable indefinitely. Nitrogen, even at polar temperatures, has a vapor pressure high enough that it would slowly sublime and escape over geological timescales. The cold trap at the poles works for water, but not for nitrogen. So water is preserved and nitrogen is not, even if both were originally delivered in similar proportions. This kind of selective cold trapping provides a natural explanation for the observed chemistry without requiring unusual delivery. Mechanisms. The carbon detection at the surface is another MESSENGER finding worth revisiting. MESSENGER identified a dark carbon-rich material coating the polar ice deposits. This material, sometimes described as a lag layer, absorbs sunlight and acts as a thermal insulator, protecting the ice beneath. Its presence suggests that the polar deposits have been there long enough for this lag to accumulate, implying that the water ice delivery to the poles predates the recent geological era. The carbon layer itself is thought to consist of organic compounds, long-chain carbon molecules that form when simpler carbon-bearing gases are irradiated by solar UV and charged particles. Similar chemistry is thought to operate in the outer solar system on the surfaces of comets and carbonaceous asteroids. Finding it at Mercury, the innermost planet, suggests that organic chemistry is more widespread in the solar system than its generally harsh environment implies. The carbon compounds at Mercury's poles are not biologically derived. They are purely abiotic, formed by radiation chemistry. But their presence demonstrates that organic chemical complexity can persist even in the most solar-irradiated region of the solar system, provided there is a cold, dark environment to accumulate it. BepiColombo carries an instrument called Symbiosis, a combined camera and spectrometer system that will image the surface at resolutions down to a few meters in some modes. Combined with the thermal infrared instrument MERTIS, This will allow the team to map the distribution of the dark lag material at the poles with much higher precision than MESSENGER achieved, to search for compositional variations within the polar deposits, and to look for evidence of fresh ice exposed by recent impacts into the polar terrain. Fresh polar ice, if found, would appear brighter than the surrounding aged material and might have a slightly different spectral signature. If BepiColombo can identify fresh ice exposures, it can constrain the current rate of ice delivery and redistribution at the poles, which feeds back into the overall volatile budget. Is Mercury currently receiving fresh volatiles from space, or is the polar ice an entirely ancient deposit that is slowly sublimating? Both scenarios are physically plausible, and distinguishing between them matters for understanding how dynamic the volatile system is today. The answer may also connect to events in recent astronomical history. A large comet impact in the last 100 million years could have delivered a significant volatile package to Mercury's polar regions. Several notable impact structures on Mercury are geologically young in the context of the last few 100 million years. If any of those impacts involved volatile-rich bodies, they could have refreshed the polar ice and introduced new chemical species into the surface and exosphere. The absence of a running clock on Mercury's surface, since there are no liquid water deposits to create sedimentary stratigraphies, makes precise dating of recent events difficult. But crater counting combined with impact frequency models can constrain the timing of major events. This connects Mercury's story to the broader narrative of how volatiles move around the solar system. Comets and asteroids are the carriers. Gravity shapes their orbits over time, sending some of them into the inner solar system where they can impact the terrestrial planets. The statistics of how often volatile-rich impactors reach Mercury versus the other inner planets depends on the dynamics of the asteroid belt and the Kuiper belt, both of which are influenced by Jupiter's gravity. Jupiter acts as both a shield, deflecting many long-period comets away from the inner system, and as a source of perturbations that can send asteroid belt bodies onto planet-crossing orbits. Understanding Mercury's volatile inventory requires understanding these dynamical statistics over geological time. That is a complex multi-body problem that planetary dynamicists are still working through, but the measurements from Mercury constrain the outcome. However much volatile material was delivered, the result is what MESSENGER found. Working backwards from those measurements toward the delivery statistics is an active area of research. The last thing to address is what Mercury's story means for the search for habitable conditions elsewhere in the galaxy. Mercury itself is not habitable and never was by any conventional definition. The temperature swings alone disqualify it, and the absence of liquid water on the surface removes the most basic requirement for life as we understand it. But Mercury's role as a case study in planetary physics has indirect implications for habitability research. Rocky exoplanets in close orbits around their host stars are common. Some of them orbit within the estimated habitable zones of cool red dwarf stars, meaning their surface temperatures might be compatible with liquid water. But whether those planets retain atmospheres, retain liquid water on the surface, or lose everything to stellar erosion is precisely the question that Mercury science helps answer. A planet in the habitable zone of a red dwarf is still receiving intense UV and particle bombardment because red dwarf stars, though cooler than the Sun, are highly active and flare frequently. The physics of volatile loss at Mercury is directly transferable to models of these worlds. The escape mechanisms, the sputtering, the photon desorption, the thermal desorption, all scaled to the local stellar luminosity and particle flux, apply to any airless or near-airless rocky body in a close orbit. If Mercury is the reference case at one stellar luminosity, measurements of the escape rates there allow scientists to scale predictions to other host stars. This is why Mercury science appears in discussions of exoplanet habitability. Mercury will not reveal whether life exists elsewhere, but it will help define the physical boundaries within which life-sustaining conditions can persist. That is a contribution that extends far beyond the boundaries of our own solar system, and it begins with a planet that was once dismissed as a dead rock and turned out to have more to tell us than anyone expected. The journey from Mariner 10 in 1974 to BepiColombo approaching orbital insertion is more than 50 years of incremental discovery, each step revealing that the simple picture was too simple, that the assumed inertness was a projection, and that the planet had chemistry, dynamics, and active processes that no one predicted. That journey is not over. The best instrumented chapter is about to begin. If you have stayed with this discussion to the end, then the science has resonated with you. The most interesting things in planetary exploration happen when reality refuses to behave the way the models predict. And Mercury has been doing that consistently for half a century. When BepiColombo's orbital data starts flowing, it will be worth watching what that data reveals. The way scientists describe what is happening at Mercury has evolved considerably over the past 2 decades, and that evolution in language reflects genuine changes in understanding. Older papers describe Mercury's exosphere as a collisionless gas in a steady state, implying a system in equilibrium where the production of atoms from the surface roughly balances their loss to space or their fall back to the surface. That description is mathematically useful, but it obscures something important. The steady state is only approximate, and the system is actually dynamic on multiple timescales. On the shortest timescale of hours to days, the exosphere responds to solar wind variations, flares, and coronal mass ejections. Sodium abundance, which is the easiest component to track because of its strong emission, has been observed to change on these timescales. During periods of elevated solar activity, the sodium density in the exosphere can increase measurably. This is consistent with enhanced sputtering and possibly with enhanced photon desorption as UV flux from the sun climbs during a flare. The system is responsive, not static. On intermediate timescales of weeks to months, the exosphere varies with Mercury's orbital phase. As Mercury approaches perihelion, the solar intensity increases, the particle bombardment intensifies, and the exospheric particle density tends to rise. As Mercury moves toward aphelion, conditions moderate slightly. The sodium tail length has been observed to vary with orbital phase, being longer and brighter near perihelion when radiation pressure is stronger and particle production is higher. The potassium tail follows a similar pattern. These orbital variations confirm that the escape processes are driven primarily by external solar inputs rather than by any internally generated source. On the longest timescale accessible to observation, MESSENGER provided a 4-year window during which the exosphere was monitored repeatedly. Over that period, systematic changes related to solar cycle were detectable. MESSENGER's operational lifetime spanned from early in solar cycle 24, near solar minimum, through the period of solar maximum around 2014. The exospheric measurements across that period show elevated particle production during the more active phase of the cycle, consistent with stronger particle bombardment driving more sputtering. Understanding the full dynamic range of the exosphere, from quiet sun conditions to active sun conditions, from perihelion to aphelion, from normal impact flux to periods of elevated micrometeorite density, requires observations spanning multiple years and multiple solar activity states. BepiColombo's expected mission duration of at least 1 year in orbit, with a possible extended mission, means it will observe Mercury across a significant portion of one solar activity cycle. Combined with the retrospective data from MESSENGER spanning a different period, the total observational baseline will eventually cover multiple solar cycles and provide a statistically robust picture of how the exosphere behaves under varying conditions. The modeling work that supports these observations has grown correspondingly complex. Early models of Mercury's exosphere were essentially one-dimensional, computing how the density of a single element varied with altitude above a uniform surface. Modern models are three-dimensional, incorporating the full geometry of the magnetic field, the spatial variation in solar wind impact, the non-uniform surface composition, the temperature gradient from day to night side, and the interaction of multiple chemical species simultaneously. These models generate predictions that can be tested against observations. When a model prediction disagrees with data, it identifies either a missing physical process or an error in the surface composition assumed by the model. The iterative process of modeling, observing, and revising has been the primary driver of progress in understanding the exosphere since MESSENGER. The same process will continue with BepiColombo data, but with better constraints, higher spatial resolution, and the ability to test the models in real time rather than post hoc. One model prediction that has not been fully confirmed yet concerns the source distribution of calcium. As noted earlier, calcium in the exosphere is best explained by micrometeorite impact vaporization rather than by the photon and sputtering mechanisms that dominate for sodium and potassium. If micrometeorite impacts are the primary source, the calcium distribution should peak in regions of elevated impact flux. The leading models predict such a pattern, but MESSENGER's limited southern hemisphere coverage meant the full spatial distribution could not be mapped. BepiColombo will test this prediction within months of establishing its final orbit. Another prediction concerns magnesium. Magnesium is less abundant than sodium in the exosphere and harder to detect, but its spectral emission lines are well characterized and in principle measurable. Models predict that magnesium should also show a distribution pattern tied to impact flux, similar to calcium. If confirmed, this would strengthen the case for impact vaporization as the dominant release mechanism for heavy species, and would have implications for the surface mineralogy. It would mean the surface contains silicate minerals with accessible magnesium that can be released by impact energy. The surface composition story is entangled with the exosphere story in ways that make separating them difficult. What is on the surface determines what gets released into the exosphere. What the exosphere contains constrains what must be on the surface. But the surface composition is known only imperfectly from remote spectral measurements, which are always an average over a spatial resolution element that is larger than the scales at which composition varies. Spectral measurements from MESSENGER had resolution elements of hundreds of meters to kilometers, which is fine for large-scale geology, but insufficient to distinguish individual mineral assemblages at the grain scale. The chemistry happening at the atomic scale, where photons are desorbing individual atoms from crystal lattice sites, operates at scales many orders of magnitude smaller than the observational resolution. This scale mismatch is a fundamental limitation. Scientists bridge it through mineralogical modeling, taking the bulk compositional measurements from orbit and decomposing them into plausible mineral assemblages that match both the measured bulk composition and the known constraints on Mercury's formation conditions. Those mineral assemblages are then used to predict which escape mechanisms should dominate and which species should appear in the exosphere. The fact that the predictions match the observations reasonably well gives confidence in the approach, but it cannot verify the mineralogy directly. The only way to directly verify the surface mineralogy is through in situ measurements on the surface itself. Mercury has never been visited by a lander. No sample has ever been returned from Mercury. The planet's mass and gravity combined with the difficulty of reaching it and the extreme surface environment, make lander missions far more technically challenging than Mars or the Moon. A Mercury lander has been discussed in mission concept studies, but has not been approved or funded by any space agency. The closest analog that has been proposed is a small impactor, which would create a fresh crater and throw up material that could be observed spectroscopically from orbit. Even this simpler approach faces significant technical challenges. In the absence of in situ measurements, the exosphere itself serves as a kind of sample return. The atoms escaping into the exosphere are real material from the surface, and their identity and abundance provide compositional information about the surface layer from which they came. In a loose sense, spectroscopy of the exosphere is as close to analyzing Mercury's surface chemistry as scientists are likely to get in the near term. This makes the exospheric composition measurements from BepiColombo not just geophysically interesting but genuinely irreplaceable. As a data source, the question of what BepiColombo will find that is new and unexpected is genuinely open. Given the history of Mercury science, which has produced surprises at every mission, it would be surprising if there were no surprises. The instrumentation is significantly more capable than MESSENGER's in several areas. The thermal infrared coverage will be global and systematic in a way it could not be from MESSENGER's elliptical orbit. The magnetic field measurements from two spacecraft simultaneously will resolve ambiguities in the field structure that a single spacecraft could not. The neutral particle detector on the Mercury magnetospheric orbiter will measure the energy distribution of escaping atoms with more detail than any previous instrument. Science tends to produce the most interesting results at the boundaries of its instrumentation capability. Lithium was at the edge of MESSENGER's capability. Elements below a certain spectral sensitivity threshold were undetectable. BepiColombo's instruments push that threshold lower in several wavelength ranges. Whatever is just below the current detection limit will become measurable. Whether that means another new element in the exosphere, a clearer picture of an existing element's spatial distribution, or a temporal variation in particle flux that was previously too rapid or too subtle to capture, something will emerge from the better data. Mercury's history of confounding expectations has shaped how planetary scientists approach small rocky bodies in general. The lesson is methodological. Do not assume that because a body is small, ancient, or in an extreme environment, you understand what it is doing. The data gets to decide. Mercury consistently returned data inconsistent with the models built to describe it, and the models had to change. That experience has made scientists more cautious about overconfident predictions for unexplored worlds. This caution is directly applicable to the growing catalogue of rocky exoplanets. When a new rocky world is detected transiting a distant star, the temptation is to classify it based on its size, density, and orbital parameters compared to known solar system analogues. If the parameters suggest something Mercury-like, the instinct is to describe it as Mercury-like, with all the assumptions that implies. Mercury's actual behavior suggests those assumptions should be held loosely. A Mercury-sized world at a similar orbital distance might be much more chemically active, or much less, depending on details of its composition and interior structure that cannot be measured from a transit-like curve. The constraints that BepiColombo's measurements will place on Mercury will become part of the library of reference, points that exoplanet scientists use when interpreting their own data. More precise magnetic field measurements, more complete exospheric mapping, better constraints on the interior structure. All of these make Mercury a tighter calibration point and a more useful reference for understanding alien worlds. It is worth stepping back and considering how unusual it is to have this kind of scientific resource available. Mercury orbits our own star. Spacecraft can reach it within a few years. Its properties can be measured directly with instruments that scientists designed, built, and can interpret with full knowledge of their calibration and limitations. The physics operating on Mercury's surface is the same physics that operates on rocky exoplanets orbiting other stars. The scale may differ, the stellar luminosity may differ, the surface composition may differ, but the mechanisms are identical. Knowing how they operate on Mercury with quantitative precision is as close as planetary scientists will come for many decades to knowing how they operate anywhere else in the galaxy. That is the deepest reason why Mercury science matters. Not because Mercury itself is remarkable, though it is. Not because the discoveries are dramatic, though they have been surprising. But because Mercury is the one place where the most relevant physics can be measured directly, completely, and at the level of detail needed to build predictive models that extend beyond it. Every atom of sodium streaming away from Mercury's surface in a tail that stretches tens of thousands of kilometers behind the planet is part of a physical process that, in some form, is stripping material from rocky worlds around every star in the galaxy where similar conditions apply. Mercury lets us watch that process happening, measure its rate, understand its mechanisms, and use that understanding to extend the reach of planetary science far beyond the bounds of our own solar system. The instruments are ready. The spacecraft is closing in. The questions are clearly defined. What comes next will be, by all scientific indications, worth knowing. There is a dimension to Mercury's scientific story that is rarely discussed outside specialist circles, and that is the history of missions that were proposed and rejected before the ones that flew. Understanding that history illuminates why the gaps in knowledge persisted for so long and why the breakthroughs, when they came, were so significant. After Mariner 10's 3 flybys in 1974 and 1975, Mercury entered a long period of scientific neglect. For nearly 3 decades, no new spacecraft reached the planet. Proposals came and went. Mission concepts were studied and shelved. The dominant explanation was cost and complexity. Mercury is difficult and expensive to reach. Its position deep in the sun's gravity well means a spacecraft must lose, not gain, energy to get there. Reaching Mars requires a simple trajectory with a modest velocity change. Reaching Mercury requires either a long series of planetary gravity assists, which adds years to the mission timeline, or a massive propellant load, which makes the spacecraft prohibitively heavy. Neither option is cheap. During the 1980s and 90s, NASA prioritized other destinations. The Voyager missions to the outer solar system, the Galileo mission to Jupiter, the Cassini mission to Saturn, and the Mars exploration program collectively absorbed the available budget for large planetary science missions. Mercury proposals that were technically sound were deferred repeatedly, not because scientists did not want to study the planet, but because the competition for resources was fierce and Mercury had a reputation as a settled question. That reputation was partly a legacy of Mariner 10. The images from those flybys showed a cratered moon-like surface. The magnetic field detection was puzzling, but seemed like a minor anomaly. The exosphere measurements were limited. There was nothing in the data that demanded immediate follow-up. Scientists who argued for a Mercury orbiter were working against a perception that the planet had already yielded its main secrets. The Messenger mission concept was developed in the late 1990s and selected as a NASA Discovery mission in 1999. The Discovery program was designed for low-cost focused missions with tightly defined science goals, and Messenger fit that framework. Its science goals were explicitly constructed around the questions that Mariner 10 had left unanswered. What is Mercury's exact composition? What is the internal structure? How does the magnetic field work? What is in the polar deposits? What is in the exosphere? The mission launched in 2004, but did not reach Mercury until 2011 because the gravity assist sequence required 7 years of transit, including flybys of Earth once, Venus twice, and Mercury itself 3 times before the spacecraft could enter orbit. This long transit time was the cost of choosing a low propellant trajectory. It was the right choice scientifically and financially, but it meant a long wait. BepiColombo, by comparison, was proposed in the 1990s as a cornerstone mission of the European Space Agency's long-range science program. It was always intended to be larger, more capable, and more expensive than Messenger, with 2 spacecraft instead of 1 and a much longer planned operational period. It was launched 14 years after Messenger and will reach orbit nearly 4 years after Messenger ended its mission. The total elapsed time from the first proposal to the first orbital science return for BepiColombo will be close to 3 decades. This timeline reflects how slowly big planetary science advances through the institutional channels of funding, approval, construction, and travel. The science questions that BepiColombo will answer were identified in the 1990s. The instruments to answer them were designed in the 2000s. The mission launched in 2018 and reaches orbit in 2026. Nearly 30 years from question to answer. That timeline is not exceptional in planetary science. It is typical. The gap between when a scientist identifies what needs to be measured and when a mission can actually measure it is routinely measured in decades. This means that the questions being formulated today about what BepiColombo will reveal in its orbital phase may not be answered by a follow-on mission until the middle of the 21st century. The institutional patience required to sustain scientific programs on these timescales is substantial, and it is rarely discussed in the popular presentation of discoveries, which tends to compress the decades of waiting into a few sentences. Understanding this timeline also clarifies why the retrospective analysis of Messenger data matters so much. Messenger ended in 2015. The lithium detection from its archival data came in 2025. The archive continues to be analyzed. BepiColombo will add its own archive when its mission concludes, an archive that future scientists will mine for a decade or more after the spacecraft is gone. The science from a planetary mission does not end when the spacecraft falls silent. It continues as long as scientists are motivated to look more carefully at the data. This cumulative character of planetary science, where each generation of researchers builds directly on data collected by previous missions, gives the field an unusual kind of continuity. The scientists who will make the most significant discoveries from BepiColombo's orbital data may not all be born yet. Their work will depend on measurements made by instruments designed by people who are now approaching retirement. Mercury's story is genuinely multi-generational in the literal sense. The historical arc from the first detection of Mercury's magnetic field as an anomaly in 1974 to the full characterization of its internal structure expected from BepiColombo in the late 2020s spans more than 50 years of cumulative effort. Each step depended on the previous one. The magnetic field anomaly motivated the theory of a partially liquid core. The partially liquid core theory predicted a specific magnetic field geometry. Messenger measured the geometry and found the north-south offset. The offset constrains the core stratification. BepiColombo will measure the higher-order field components that further constrain the stratification model. Each measurement makes the next one more informative. This is science in its most recognizable form. Hypothesis, observation, revised hypothesis, better observation, tighter constraint. The timescale is compressed in textbooks and expanded in reality. The actual experience of doing it takes a career, or multiple careers, to traverse. Mercury rewards that patience because it is strange enough to keep generating genuine surprises. A planet that was understood to be dead revealed a magnetic field it should not have. A planet stripped of volatiles retained sulfur, sodium, lithium, and water ice. A planet too small to have active geology has surface features still forming today. Every assumption that proved false required new physics or new chemistry to replace it. And every piece of new physics has connections to problems that extend far beyond the planet itself. The volatile detections connect to planetary formation theory. The magnetic field connects to the physics of metallic dynamos in small bodies. The hollow formation connects to surface chemistry under UV and particle bombardment. The polar ice connects to volatile delivery and cold trapping across the solar system. None of these threads is isolated. Mercury sits at the intersection of multiple active research programs in planetary science, and it provides constraints that no other solar system body can supply. That is why, when the BepiColombo mission returns its first high-quality orbital measurements, the scientific community's attention will be substantial. Not because Mercury will suddenly dominate headlines in the way that Mars missions sometimes do, but because the data will immediately propagate into theoretical papers on planetary interiors, exosphere physics, surface chemistry, magnetospheric dynamics, and planetary formation. The ripples of a single well-designed planetary mission extend far through the scientific literature. Mercury has been the most consistently surprising planet in the solar system. It has violated expectations more reliably than any other world. Its behavior has forced revisions to models of planetary formation, magnetic field generation, surface chemistry, and volatile retention. None of those revisions are complete. The open questions are real, specific, and answerable in principle. For anyone following planetary science, Mercury's next chapter is one of the most anticipated in the field. The instruments are in flight. The timing is right. The questions have been accumulating for decades. The answers are coming. One of the more philosophically interesting aspects of Mercury science is the question of what it means for a planet to be active. That term is used loosely in popular descriptions of planets, often implying volcanoes, tectonics, or obvious geological change. Mercury has none of those in the present era. Its volcanic activity ended approximately 3 billion years ago. Its tectonic regime shifted from one of compression and contraction driven by core cooling to a near-static state. By the conventional criteria, Mercury is geologically inactive, and yet it is not passive. The surface is being chemically and physically processed every second. The exosphere is being produced and replenished continuously. New surface features called hollows are forming on timescales that are geologically rapid. Polar deposits are being maintained in dynamic equilibrium between delivery and loss. The magnetic field is being sustained by an interior that is still conducting and partially convecting. None of these processes would appear on the checklist that a textbook description of geological activity would include. They are subtler, slower, and driven by external inputs rather than internal heat. But they are real, ongoing processes, and they produce measurable, changing states in the planet's surface and immediate environment. Mercury is a case study in the distinction between geological inactivity and physical quiescence. It has the former without the latter. This distinction matters for how planetary scientists categorize worlds more broadly. The conventional categories, active versus inactive, geologically alive versus dead, tend to be defined by visible geological features like volcanoes, mountains, and tectonic rifts. These features require internal heat. A world without them seems quiet. But planetary activity at a surface level can be driven by external inputs from the stellar environment, and that kind of activity does not require internal heat at all. Venus and Mars demonstrate different points along this spectrum. Venus has active volcanism, thick atmosphere, high surface temperatures, and ongoing geological resurfacing. It is clearly geologically active by any measure. Mars has neither volcanoes currently erupting nor significant tectonic activity, but it has seasonal atmospheric processes, dust storms, and ongoing surface erosion by wind. Mercury has none of those either, but it has a qualitatively different set of active processes, driven entirely by solar input. The three planets represent three distinct modes of planetary activity in the mid to late life of a rocky world, and understanding Mercury's mode is essential for building a complete picture of how rocky planets evolve. The terminology used in the scientific literature has evolved to capture this. Rather than describing Mercury as inactive, researchers now typically describe it as externally driven or solar wind dominated in terms of its surface processing. These terms better capture the physics. The energy input that keeps the surface dynamic does not come from the interior, but from outside the planet entirely. This is a physically meaningful distinction that affects everything from the chemical inventory of the surface to the rate of volatile loss to the morphology of surface. Features like the hollows. The hollow formation mechanism is a particularly good illustration of this point. Hollows are driven by sublimation of subsurface volatiles, which requires energy. That energy does not come from below. There is no magma, no hydrothermal heat, no geothermal gradient sufficient to drive sublimation at the temperatures involved. The energy comes from above, solar radiation and particle bombardment, reaching shallow depths into the crust and heating the topmost few centimeters of material enough to allow volatile escape. It is an entirely surface-down process, not an interior-up one. This inverted energy flow, from the stellar environment inward rather than from the planetary interior outward, may be the defining characteristic of rocky bodies in close stellar orbits at late stages of their geological evolution. Once internal heat is gone, the surface does not go quiet. It enters a different regime, where the external environment becomes the dominant driver of change. Mercury is the nearest and best studied example of this regime, but the physics applies anywhere that a small rocky body orbits close to an energetic star. The chemical consequences of this inverted energy flow are extensive. When energy flows from the interior outward, as in a volcanically active world, it tends to bring reduced chemical species to the surface: sulfides, carbonates, silicates, carrying elements from the deep mantle. When energy flows from the outside inward, it tends to oxidize the surface, disrupt bonds, and selectively remove the most volatile species. Mercury's surface is in the outward erosion regime, and that shapes its chemistry in specific ways that distinguish it from volcanically active worlds. The high surface reflectance in hollow regions, the bright halos around those features, is consistent with the removal of darker, more absorbing volatile compounds and the exposure of fresh, lighter silicate material beneath. This reflectance pattern is a spectral marker of the externally driven erosion process. Similarly, the depletion of the most volatile elements from the equatorial surface regions, while those elements persist in cooler high-latitude zones, reflects the temperature-controlled selectivity of the escape mechanisms. The surface carries a record of its exposure history, written in its chemical composition and reflectance. Reading that record is one of the primary goals of BepiColombo's spectroscopic instruments. The combination of imaging and spectroscopy at multiple wavelengths will produce compositional maps of the surface at higher resolution and more complete coverage than anything MESSENGER achieved. Those maps will show where volatile rich regions persist, where they have been depleted, and how those patterns correlate with latitude, solar exposure, and proximity to geologically distinctive features like impact craters and volcanic terrains. The volcanic terrains, even though they are 3 billion years old, retain compositional signatures of their origin. MESSENGER identified regions of high sulfur concentration associated with ancient volcanic flows, and these regions also tend to show higher hollow density. The connection makes physical sense. Volcanic flows that brought sulfur-rich material to the surface created concentrations of volatile bearing minerals in the outer crust that are still being slowly depleted by the ongoing surface erosion processes. The ancient volcanism set up the chemical inventory, and the modern external erosion is slowly removing it. This connection between ancient geology and modern chemistry is another dimension of Mercury's complexity. The planet's current behavior is a function of its formation, its history of volcanism, its subsequent cooling, and its ongoing exposure to the solar environment. Disentangling those contributions requires measurements at multiple scales and multiple levels of chemical sensitivity, which is precisely what BepiColombo is designed to provide. There is also the question of how Mercury's obliquity, its axial tilt, contributes to its behavior. Mercury's axial tilt is less than 1 degree, essentially 0. This means that the Sun never rises significantly above the horizon at the poles, and polar crater floors remain in permanent shadow without any seasonal variation. On Earth, the axial tilt of 23.5 degrees creates seasons and moves the sub-solar point from tropic to tropic across the year. On Mars, the tilt of 25 degrees similarly creates seasons. On Mercury, there are essentially no seasons. The subsolar point stays within 1 degree of the equator throughout the entire orbit. This near-zero obliquity is probably not an accident of formation. Tidal forces from the Sun, acting over billions of years, have damped Mercury's obliquity from whatever initial value it had at formation to its current near-zero state. The same tidal forces that produce the 3:2 spin-orbit resonance also work to flatten the axial tilt. Both effects are expressions of the Sun's gravitational dominance at Mercury's close orbital distance. The near-zero obliquity has a direct effect on the polar cold traps, because the Sun never rises high at the poles, and because Mercury has no substantial topographic relief that would cast shadows at lower latitudes. The permanently shadowed regions are confined almost entirely to the floors of polar craters. The cold trap geometry is therefore set by the crater distribution rather than by topography. Craters are more or less randomly distributed at the poles, which means the cold traps are a patchwork of isolated ice deposits rather than a continuous polar cap like what Mars and Earth have. The total area of these cold traps, and therefore the total ice inventory, depends on the depth and size distribution of the polar craters. MESSENGER mapped the northern polar region extensively. BepiColombo, with its better southern hemisphere coverage, will complete the global picture. The southern polar ice inventory may differ from the northern, either because of differences in crater density or because of differences in the history of ice delivery to the two poles. Knowing both is needed to estimate the total planetary water ice budget accurately. That budget, even if it turns out to be relatively small in absolute terms, has scientific importance. It constrains the total amount of water delivered to the inner solar system by cometry and asteroidal bombardment. Mercury, sitting at the inner edge of the region where these deliveries could be efficiently trapped, provides a minimum estimate. Earth and Venus received similar or greater bombardment, but had very different geological histories that reworked any original volatile delivery. Mercury's cold traps preserved a fraction of the delivery without significant alteration, offering a sample of the ancient delivery flux in a form that can still be measured. All of these threads converge on the same conclusion. Mercury is a scientifically rich world whose full complexity was not recognized until MESSENGER changed the picture, and whose full characterization requires BepiColombo's systematic survey from orbit. The planet does not make headlines the way Mars does. It does not have the dramatic ring system of Saturn or the icy moons of Jupiter. It does not have seasons, erosion, or weather in any familiar sense. What it has is a form of ongoing activity that is quieter but no less interesting from a physics standpoint. It has a chemical story written in its surface and exosphere that connects to planetary formation, volatile delivery, solar-wind interaction, magnetic field generation, and the long-term evolution of rocky worlds. It has a geological record that preserves processes from the earliest solar system alongside evidence of changes happening today. It is the innermost, smallest, most eccentric, most extreme of the classical planets, and it has spent decades proving that those superlatives translate into scientific value. The next installment of Mercury's story begins when BepiColombo settles into its final orbit and the instruments start returning data from a position only a few hundred kilometers above the surface. At that point, years of instrument development, years of transit, and years of preparation by a large international science team will converge on a data set that is, in every measurable way, the best look at Mercury that humanity has ever taken. What that data will show is, in the best sense of the phrase, genuinely unknown. Given the track record, it is likely to include something that the models did not predict. It is likely to raise new questions alongside answering old ones. It is likely to add new elements, new processes, or new constraints that reshape the current picture in ways that cannot be anticipated. That is the nature of planetary exploration when it is done well, and when the target is as complex and surprising as Mercury has proven itself to be. The smallest planet is also, scientifically, one of the most informative. That is the finding that has accumulated across 5 decades of observation, from Mariner 10's first grainy images to the lithium detection in 2025, and it will continue to accumulate as long as scientists keep pointing instruments at this quietly remarkable world. The question of whether Mercury will ever be visited by a lander is worth addressing directly, because it frames the long-term future of Mercury science and helps explain why orbital and flyby missions have been the dominant strategy for studying the planet. A Mercury lander would face engineering challenges that are qualitatively different from landing on Mars or the Moon. The most severe is thermal. On the dayside equator, ambient temperatures exceed 400 degrees Celsius, which exceeds the operating range of most conventional spacecraft electronics. The materials used in standard spacecraft construction, aluminum alloys, standard solar panel materials, most electronic components, all have operational limits that fall below the dayside surface temperature. A lander would need either to operate only at night, during a 176-day-long thermal cycle, or to use specialized high-temperature electronics and thermal shielding, far beyond what has been developed for any previous mission. The second challenge is communication. Mercury is close to the Sun, which means it is rarely visible from Earth at large angular separations. Communication windows, when the planet is far enough from the Sun to allow reliable radio contact, are limited. A lander operating at night would have to store data during the long darkness and transmit during favorable windows, placing significant demands on onboard storage. The third challenge is the radiation environment. Mercury's proximity to the Sun exposes any surface hardware to particle radiation at levels far higher than at Mars or the Moon. Extended surface operations would require significant radiation hardening of all electronic components. Given these challenges, a Mercury lander has historically been evaluated as extremely difficult with current technology, but not impossible in principle. Some mission concept studies have explored the idea of a lander that would touch down in a permanently shadowed polar crater, where temperatures are stable at -200 degrees Celsius and radiation exposure is lower. Such a mission would avoid the thermal problem, but would introduce different challenges around lighting. Since solar power is not available in permanent shadow and around mobility, since the crater floor terrain may be rough, in such a scenario, the lander's primary scientific value would be in situ chemical analysis of the polar ice and the surrounding regolith, which would provide the direct compositional measurements that spectroscopy from orbit cannot supply. The isotope ratios of the water ice, the identity of the organic lag layer compounds, the trace element chemistry of the frozen material, all of these could be measured definitively from the surface in ways that are not possible remotely. The scientific return would be high. The technical challenge would also be high. Whether a polar lander mission will be approved and funded in the coming decades depends on how the planetary science community prioritizes Mercury relative to competing targets. What BepiColombo's orbital results reveal about the specific science questions that require in situ data to answer, and what advances in spacecraft thermal management and radiation hardening become available through other technology development programs. The discussion of Mercury lander concepts is a useful reminder that the current BepiColombo mission, as ambitious as it is, represents an intermediate step in the long-term scientific exploration of the planet, rather than a final chapter. The questions it will answer will motivate new questions. The constraints it will tighten will reveal which remaining uncertainties require more direct measurement to resolve. Mercury science will outlast BepiColombo, just as Mercury science outlasted Messenger and Mariner 10 before it. The planet will continue to shed material into space. The hollows will continue to grow at their slow rate. The polar ice will continue to sit in the dark. The magnetic field will continue to deflect the solar wind. And scientists will continue to find new ways to measure these processes more precisely and to extract more information from the data they have already collected. In the context of solar system exploration, Mercury occupies a peculiar position. It is close enough to be reachable, extreme enough to be scientifically valuable, and complex enough to remain only partially understood despite more than 50 years of study. That combination of accessibility, extremity, and complexity is rare. Most bodies that are easily reachable have yielded their main secrets by now. Most bodies that are extreme enough to still be surprising are difficult to reach. Mercury is both accessible and still surprising, and it will remain so for the foreseeable future. The sodium tail visible in images from ground-based telescopes is a striking visual summary of what Mercury science has revealed. A planet losing itself, atom by atom, into space. The tail is real, persistent, and caused by completely understood physics. It is not dramatic in the way that a volcanic eruption or a spacecraft landing is dramatic, but it represents something genuine, a direct observation of a planetary process that runs continuously and connects the smallest scales of atomic physics to the largest scales of planetary evolution. Every sodium atom in that tail was once part of a mineral grain on Mercury's surface. It was bound in a crystal lattice sitting in sunlight until a photon struck it with enough energy to free it from that lattice. It then escaped Mercury's gravitational pull because the planet is small and the atom is light. It was pushed away from the sun by radiation pressure because photons carry momentum and the atom is small. It traveled for hours or days, gradually spreading out from its initial trajectory until it either collided with another particle and was lost or eventually was ionized by the solar wind and swept into the heliosphere. That journey from mineral grain to escaping atom to particle in the solar wind is one of the simplest possible planetary processes. It requires no geology, no chemistry more complex than bond breaking, no internal heat, no atmospheric chemistry. It requires only a rocky surface exposed to sunlight. which describes billions of small bodies throughout the galaxy. Mercury is the nearest, largest, best characterized example of this process, and it has a tail to show for it. That tail was always there, visible in principle, but not seen clearly until scientists thought to look with the right instruments tuned to the right wavelengths. When they did, they found not just the sodium, but the potassium, the calcium, the magnesium, the hollows, the ice, and now the lithium. Planetary science rewards the careful look. Mercury has been teaching that lesson since 1974. The broader context of inner solar system science in which Mercury sits is worth one final consideration, because it places the planet's significance in the largest possible frame. The inner solar system, the region from the Sun out to the asteroid belt, contains 4 terrestrial planets: Mercury, Venus, Earth, and Mars, each formed from the same reservoir of raw material in the early solar disk. Each has followed a different evolutionary path over the past 4.5 billion years, shaped by its mass, its orbital distance, its accretional history, and its subsequent geological and atmospheric evolution. Together, the 4 planets form a comparative dataset that planetary scientists use to test models of how rocky worlds evolve. Venus is the planet most similar to Earth in size and composition, yet it has a thick, crushing atmosphere of carbon dioxide, surface temperatures of 465 degrees Celsius, and no evidence of plate tectonics. Understanding why Venus diverged from Earth so dramatically requires understanding the physics of atmospheric runaway greenhouse effects, volcanic outgassing, and atmospheric escape. Mercury provides a crucial data point on the opposite end of the spectrum. What happens to a rocky world that has lost everything it ever had in the way of atmosphere and is being slowly stripped of its surface chemistry? Mars occupies a middle ground. It has a thin atmosphere, evidence of ancient surface water, frozen polar caps, and geological structures that span billions of years of activity, followed by progressive shutdown. Mars has been the focus of intense exploration, partly because of its potential relevance to the question of habitability, but also because it represents the endpoint of a geological trajectory that Earth itself might eventually reach on a sufficiently long timescale. Mercury represents a different endpoint entirely. The rocky world that forms close to a massive star accretes a disproportionate amount of metal, loses its volatiles early but not entirely, sheds its atmosphere, and settles into a state of slow external erosion driven by the star's radiation and particle output. This trajectory may be more representative of the most common rocky planets in the galaxy than Mars's trajectory is, because close-in rocky planets appear to be common in the census of exoplanets, while Mars-like planets at intermediate orbital distances around Sun-like stars may be less ubiquitous understanding. Mercury therefore gives planetary scientists a framework for interpreting a large population of worlds they can observe only indirectly. Every measurement from BepiColombo that constrains the rate of volatile loss, the exospheric composition, the magnetic field structure, or the surface chemical evolution of Mercury becomes a calibration point for models that apply to thousands of exoplanets that will never be visited by any spacecraft. This is the full scope of why Mercury science matters. Not because of any single discovery, however unexpected. Not because of any single mission, however capable. But because of the cumulative picture built up over 50 years of observation, analysis, and progressive refinement of understanding. Mercury is the inner solar system's harshest environment, its most extreme planet, its most surprising world, and its most instructive reference point for the physics of rocky bodies under stellar influence. The planet will not stop being surprising. The science will not stop advancing. The instruments are better than they have ever been. The data pipeline is the most capable, yet designed for this target. And the community of scientists working on Mercury is larger and more interdisciplinary than at any previous point in the history of planetary exploration. What started with Mariner 10's detection of an inexplicable magnetic field in 1974 has grown into one of the most scientifically rich programs in planetary science. Mercury was supposed to be the least interesting planet in the solar system. It has turned out to be one of the most rewarding to study, precisely because it refused to behave as expected. That refusal continues. The lithium is there. The hollows are growing. The tail is streaming. The ice is preserved in the dark. The magnetic field is offset in ways that still need explaining. And a spacecraft is closing in on orbit, ready to make the most comprehensive measurements the planet has ever received. That is where the science stands. the story is not finished. It is, in the most accurate sense of the phrase, actively ongoing. One last observation that brings the full scope of Mercury science into focus concerns the very definition of what it means to study a planet. In the popular imagination, studying a planet means sending a spacecraft, taking pictures and reporting what is there. That framing is not wrong, but it is incomplete. The most important work in planetary science happens in the years after the spacecraft returns its data, when researchers with different expertise attack the same dataset from different directions, build competing models, test those models against the data, revise them, publish their findings, and argue about the implications. The data from Mariner 10 was still being reanalyzed decades after those flybys. The data from Messenger is still generating peer-reviewed publications 10 years after the spacecraft ended its mission. The data from BepiColombo will almost certainly be generating discoveries for 20 or 30 years after the mission concludes. This extended, scientific life of planetary data is one of the most valuable and underappreciated features of robotic planetary exploration. When a mission returns gigabytes of surface images, spectra, magnetic field measurements, and particle flux data, the first pass of analysis by the mission team captures the most obvious findings. But the subtler signals, the unexpected correlations, the trace abundances at the edge of instrument sensitivity, often take years of additional work to extract. The lithium detection from Messenger is a perfect example. The signal was in the data from the beginning. The tools and attention needed to find it came later. Mercury will continue to reveal new things from existing data for as long as scientists are motivated to keep looking. BepiColombo will add an entirely new archive, richer and more complete, that will support another generation of discoveries after its orbital mission concludes. The planet that seemed finished, understood, settled, and unremarkable has proven to be none of those things. It will continue to reward curiosity and careful analysis for decades to come. That is perhaps the deepest lesson Mercury teaches. Completeness in planetary science is always provisional. The assumption that a world has been characterized, that its major features are known, and its behavior is understood, has been proven wrong too many times to be held with confidence about any world. Mercury demolished that assumption most thoroughly of all. It will likely do so again. If you want to be among the first to hear when BepiColombo's orbital results come in, and when the next unexpected finding from Mercury is published, subscribing ensures you will not miss it. The data is coming. The science is already underway. And Mercury, as always, is unlikely to behave exactly as expected.